So real quick, before we actually start talking about the law of cosines again, I want to reiterate what I talked about in the email I just sent this morning, the Canvas announcement. So our plan for the rest of the semester, since we went through chapter 9 quicker than normal, we're going to finish early. Okay? So we're doing 10.2 and part of 10.3 today. We're doing more on Wednesday and more on Friday. But realistically, we only have 3 days of lectures left. Okay? And then next week, we'll spend Monday reviewing for those who want to review. Again, optional. And then next week, Wednesday, will be your final exam, which is going to be cumulative. All right? So that's kind of the outlook for the rest of the semester. We're almost done. So yeah, there's only 2 examples left to do in 10.2, but they kind of take a while. But they're example problems or application problems. So let's get started. If there are any questions about what's going on for the rest of the semester, again, the next week and a half, now is a great time to ask them. Otherwise, we're going to start talking about this example from the text. Yeah, we have nice windows in that classroom. I like that one. Far from my office, though, which kind of sucks. Okay, so example 3, what we're going to do right here. This is going to be from the book. And I'm not going to write it all down because it's pretty long. So if you're following along and making your own notes, which is good, just write from the book right now because you're not going to have time to write this all out. We're just going to look at it together and see what we have here. So example 3, using the law of cosines to solve a communication problem. So what this problem is, we're just kind of going to read it. I'll read it and we'll kind of talk about it before we get into the math. So on a lot of cell phones with GPS, you can get an approximate location before the GPS signal is actually received. So it's accomplished through triangulation, which works by using the distance from 2 known points. Okay, so suppose there are 2 cell phone towers that are within range of the cell phone, and those 2 towers are located 6,000 feet apart from each other along a straight highway running east to west. And the cell phone is north of the highway. The question is, based on the signal delay, it can be determined that a signal is 5,050 feet from the first tower and 2,420 feet from the second tower. Determine the position of the cell phone north and east of the first tower and determine how far it is from the highway. So, if you are a really, really good reader and a very, very good person at seeing things visually, I'm sure you already know what's going on here. But for most people, you probably read through that whole problem and know nothing. Okay? You need to draw a picture. Take things one at a time. We draw a triangle. Yeah. Surprise, surprise in trigonometry. All triangles and circles, mostly triangles. Okay, so we just need to parse each piece of information and add each piece of information to our triangle. So let's go blah, 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 blah. 2 cell phone towers. That's going to be important. The 2 towers are located 6,000 feet apart. Let's use this. 2 towers are 6,000 feet apart along a straight highway, east to west. Cell phone is north of the highway. So what we have right here is we have 2 towers, 6,000 feet apart. Maybe a tower here, a tower here. This is 6,000 feet apart. A little over a mile. Okay? So we also were told that the cell phone is north of the highway somewhere. I don't know where it is. It's north somewhere. Let's just say it's here. So again, this will be the phone. This will be the tower. This will be another tower. Okay, so then we go back to the problem. What else do we know? Based on the signal delay, the signal is 5,050 feet from the first and 2,420 from the second. So we just add that. This distance right here, 5,050 feet. This distance right here, is 20 feet. And goodness, what do we got right here? We got a triangle that's not a right triangle. We can use the law of cosines. We can't use the law of sines, remember. Law of sines is going to be no good here because for law of sines, we need an angle and its opposite side. And we have no angles here. Okay, let's go back to the problem. What else do we know? We incorporated this feed information. Determine the position of the cell phone north and east and determine how far it is from the highway. How far is it from the highway and what the position is. Okay, so it's kind of unclear, but how far the highway, that's this. How far it is from the highway. Position, it's probably just asking what the angle is. Okay. Yes, that is definitely what it's asking. It's asking what this angle is. So we need to find theta and x. Oh, 2420? You're right. Thank you. Good catch. So, as soon as you spend, the 5 minutes trying to figure out what the heck this problem's even talking about, this is really just a problem like every other problem we've done in this section. We need to use the law of cosines to find this angle. Okay. And again, when you're using the formula for law of cosines, it's a good idea. And you don't have to do this, but it can be a good idea to put everything in terms of A, B's, and C's. Okay? You don't have to. If you can immediately use the formula right now, go ahead. But let's just call this A, call this B, let's call this C. Optionally. Right? And then we need to use the version of this that lets us have theta. So the version for theta is the one where theta is opposite the left-hand side. So let's open real quick our law of cosines sheet. So we can look at the three formulas right here. Okay, whoa. Hello, cat. So law of cosines right here that you have access to. We have three of them. And notice that the left-hand side is always the squared side or the angle on the right. The opposite angle. So if we're solving for theta right here, the left-hand side should be B. So that's the one we're going to use. We're going to use the one where the left-hand side is the opposite side from the angle that we want, which in this case is this formula. So we just write it down again. B squared to the A squared plus C squared minus 2AC cosine of B. Again, B in this case is theta. You could write B or theta as you prefer. And you just plug things in. So, how long are you going to stand there, cat? Don't mind the tail. And you just plug things in. So B we said was 2420. It's equal to A we said was 5050. Plus C squared, 6,000. Minus 2A, which we said 5050. Times 6,000. Again, it's always going to be the same thing. Cosine of theta. And again, if you want to solve for theta and have that added to your formula sheet, go for it. But I'm just going to solve for it every time. So we subtract these two things. We get 2420 squared minus 5050 squared. We're just solving the equation. Minus 6,000 squared. And then we have to divide by the coefficient, -2, times 5050 times 6,000, just like we've done before. And that's cosine of theta. So we take the inverse cosine of both sides. And what we're going to get, take the inverse cosine of both sides, you're going to get, well, again, just show you, typing it in all at once, make sure you use your parentheses correctly. The inverse cosine of the numerator, 2420 squared, minus 5050 squared, minus 6,000 squared, divided by the denominator, which is -2 times 5050 times times 6,000. All right, and then again, make sure it's in the right thing. So it needs to be in degrees here. And you're going to get 23 .3281 degrees. All right, or again, about 23.3 degrees. So, we've done all the hard part. We needed to find theta and x. We found theta. Now let's use that to find x. So we're just going to look at this part of the triangle. Okay? To find x, we don't need the whole triangle. Let's just look at the right triangle now. Right? This is still 50-50. Oops, I missed my 3. This right here is still 23.3 degrees. This right here is still, no, this is not 6,000, right? 6,000 is this whole distance. We're just looking at this little right triangle. And we are all the way back at the beginning of, we're all the way back to the beginning of class, chapter 7. We've solved these things before, okay? So this is a right triangle. So we can use trig. Sine of this angle is x over 50-50. Sine of 23.3281 degrees equal to x over 50-50. So just multiply both sides by 50-50 and you're going to get that x is approximately equal to 50-50 times the sine of 23.3281 degrees, which is approximately 1,999.8. So realistically, about 2,000 feet. Okay. And that's our answer. All right. And that's how you do these problems. Any questions on this before we go on to the next example problem? One more application before we move on to polar coordinates. Good. Brock has a question. So I skipped some steps, right? But we just multiplied both sides by 50-50 to get 50-50 times the sine 23.3 degrees equals x. And then I just type this left-hand side into my calculator. Skipping a little bit of algebra, but it's good to ask if you're curious. I'm assuming that was your question. Also, let's do an early attendance question today. For our attendance today, give me... We'll do colors again because I'm losing my creativity. For our attendance question, send me on Discord just a color. Okay, and you'll get your attendance points for today. Then we'll move on to example 4. Doesn't have to be your favorite color. Could be your least favorite color. Just a color. Then we're going to do example 4. So, example 4 gives you a picture, and there's a little bit of writing, so we'll just write it down. It won't take too long. But suppose a boat leaves port, goes 10 miles, turns 20 degrees, and travels another 8 miles. Question is, how far is it from port? And now this one's kind of funny because the triangle that you get actually doesn't have that 20 degrees. Like, you might think the 20 degrees is in the triangle, but it's actually not. You have to use a little bit of geometry. Okay, so let's say we have our port right here. And then the boat is going 10 miles. It doesn't specify the direction, but let's say it goes this way. Oh, another small thing, by the way, about the other problem is please remember to use units right here. Our angle is in degrees. And the distance, how far are we from the freeway? About 2,000 feet. The units are very, very important. and are worth points. Okay? And then it turns 20 degrees. So that means, right, if you're only turning 20 degrees, that means you're only turning a little bit. But that means that angle is still really big. So it actually looks kind of like this, right? And this is not 20 degrees. The 20 degrees is this. Okay, so careful for that. 8 more miles. And the question is, how far is it from port? And the answer is whatever that distance is. Kind of a curvy, little side of that triangle. Okay, so what do we have? We want to look at this solid triangle. We have an angle, sort of, and we have 2 sides. But again, we don't care about this 20 degrees. This 20 degrees is not helpful. That's 20 degrees in some other triangle. We care about this big angle. So if this is 20 degrees, we need to find out what the big angle is. So again, remember back to your geometry days. We haven't really talked about this. What is this big angle and how do we find it? Yeah, exactly. It's 160 degrees, right? Because this, if you add both angles up, you get 180 degrees. So they are supplementary angles. All right, and the 160 degrees is the one that we really care about. So we've got a side, we've got an angle, we have another side. Again, can we use law of sines? I like law of sines. I think it's easier. So I like to check law of sines. To use law of sines, we need an angle and its opposite side. But we only have one angle. We certainly don't know the opposite side. This is what we're trying to find. Okay, so we need to use law of cosines. And again, for law of cosines, I really like naming things A, B, and C. Because when I name things A, B, and C, it makes it easier for me to use the formula. Right? Because these formulas, as given to you, have A's, B's, and C's. Okay, so you can name them anything you want. Let's call this A, let's call this B, let's call this C. And so we need to use a formula that's solved for C. C is the thing that we want. You don't have to name them, but you can. So we consult our formula sheet. We want to use the C1. So C squared is A squared plus B squared, almost Pythagorean theorem, minus 2AB cosine of its opposite angle. Okay, so again, it's a really good practice when you're using a formula. This is true for quadratic formula, law of sines, law of cosines. It's really good practice when you're using a formula to write the formula down first without any numbers. It helps you plug in and it helps give partial credit. So again, we want to use the formula C squared is A squared plus B squared minus 2AB cosine of the opposite angle C. We've been using gamma. Right? And then just plug things in. So C squared is A squared, so that's 10 squared or 100, plus B squared, 64, minus 2 times 10 times 8 times the cosine of that angle, 160 degrees. So if you want to simplify, you can. Or we could just take the square root of both sides and type it into our calculator, right? Again, normally when you take the square root, you need a plus or minus. But C is not going to be negative, so we're just not going to have the minus. How do you pick an opposite angle when the known angle is in the middle like this? So when I say opposite angle, so 2 things. For law of sines, you pick an opposite angle that you know the opposite side of. But again, the only angle we have is here, and we don't know its opposite side. For law of cosines, this angle is always the opposite angle of whatever this side is. So if we're solving for C, we need this angle. Okay? If we're solving for this side, we need this angle. Otherwise, it cannot be solved with the law of cosines. Okay? I don't think I totally understood your question, so feel free to clarify. So, oh, I see. So, I called it gamma. You can call it whatever you want. Again, you don't even have to be naming these things. I just like naming these things so they fit with my formula. And gamma is always opposite C. alpha is always opposite A, and beta is always opposite B in naming conventions. So if this is the side B, what we would call this angle beta. If this is the side A, we would call this angle alpha. And that's just convention, but really you can kind of call it whatever you want. But in these formulas, A and A, this is like our alpha. These are the opposite angle on opposite sides. B and B, or beta, are the opposite side and angle. C and C, or gamma. Okay. Good question. So we just type all this stuff into our calculator and see what we get. All right. We need to type in square root of 10 squared, or 100, plus 8 squared minus 2 times 10 times 8 times the cosine of 160 degrees. We get 17.73 approximately. And what are our units? Our units are miles. And again, most people hate application problems, but there's a super big advantage to application problems is when we get our answer, we can stop and think for a moment. Does this answer make sense? If I'm on a boat and I go 10 miles and then I turn 20 degrees to the side and go another 8, should I be 17 miles away? And sure, that seems like a reasonable answer. It seems like a reasonable situation. If we got that we were 20 miles away, that would literally be impossible, right? We can't be more than 18 miles away. Because I know I could get there in 18 miles just by going exactly the way I came. But we're taking a shortcut, so it should be something a little smaller than 18. I'm actually personally surprised. I don't have a lot of experience with this sort of thing. I'm personally surprised that it's so close to 18, but it's still a reasonable solution. So always check that your answer is reasonable. All right. So that's the section. That's the law of cosines. The harder problems for law of cosines by far for almost everybody is going to be things like example 3, where you have all the sides and you need to find the angle. These ones are a little trickier because then you have to do a lot of algebra to solve for that angle. Okay, so just make sure you do some practice for the quiz on Wednesday. Your quiz is only going to be on 10.2. We're starting 10.3 today, but it won't be on the quiz because we won't be finishing it. So make sure, even if you're not doing the whole homework assignment, do a couple problems where you have all 3 sides, because these ones are the trickier ones. Watch out for the all 3 sides situation. Okay, be careful with your algebra. These ones are a little simpler when you have an angle and only need to solve for a side, because then it's kind of already in the right format. All right, any other questions before we move on to 10.3? I mentioned that chapter 10 really is kind of a hodgepodge of stuff, and now we are really going to be jumping to a weird place. And yeah, the college has some cool outdoor classes. I found out that they used to have even more. Like they even had like an outdoors degree or something, but due to like funding and demand or something, I think it was cut a few years ago. But they're pretty cool. I want to take some more myself. All right, so we're really jumping way out in the middle of nowhere with polar coordinates, but polar coordinates are going to include trig, so it makes sense. It's a natural extension, an application of this trig that we've been talking about, okay? And furthermore, we get into some really cool stuff. The last section that we're doing, we're going to start it on Wednesday, finish it on Friday. The last section that we're doing in this class is relating trigonometry, polar coordinates, and complex numbers. And there's some really cool stuff that you can get into once you go down into the deep end of that material. We're not going to go to the deep end of that. We're just going to kind of do an introduction of, hey, here's some cool stuff, and here's some here's how this stuff sort of works. And it's pretty neat when we get into 10.5. So really this is just a warm up for 10.5. Okay. So most of you, I imagine, have seen polar coordinates before, and we're not going to be going super heavy into them. This is a pretty light section. Okay. You just have to essentially know what they are. Okay. So polar coordinates, instead of an XY system where we go, okay, we're right X and we go up Y, polar coordinates talks about radii and angles. So on your polar grid, you just have a bunch of concentric circles, and I don't need anyone to buy like polar paper or anything. Okay. Because we really aren't going to be using it that much. You can just make one of your own. It doesn't have to be pretty. The idea is just, do you know what this is? Okay. Doing things by hand can be useful, but really it's just a testing whether you know. So any point on this polar grid is a radius. So anything on here is radius 1, right? This is a unit circle. Anything on this last one is radius 5. So any point is just, what's your radius? 5, 4, 3, 2, 1. And what's your angle? Okay. So these points are of the form r comma theta, radius and angle. Usually we find the angle first. So like if it were pi over 4 is our angle, we'd say, okay, we're somewhere in this direction, 45 degrees. Is our radius 1, 2, 3, 4, 5, somewhere in between. We'll plot that way. So let's just get right into it. Example 1. Plot on the same polar grid. Part A, the point 3 comma pi over 2. So this is a point with radius 3 and angle pi over 2. So pi over 2 is 90 degrees. Pi over 2 means that we're going to be somewhere over here, 90 degrees. What are all the points with 90 degrees? They're over here. And we need to select the specific one with a radius of 3. We go 1, 2, 3. We'll label that point A because it's part A, right? And that's what polar coordinates are right here. Okay. So part B, -2, oops, sorry, jumping ahead, +2 and pi over 3. We do this the same way we did part A. Say, okay, where's the angle pi over 3? Pi over 3 is 60 degrees. So it's like somewhere here is our angle, 60 degrees. And we just need to find the one with radius 2. So this is the circle with radius 2, right? Radius 1 circle, radius 2 circle, radius 3 circle, 4, 5. Okay. And that's all we're doing here. Can look a little different if you get something like part C, -2 and pi over 6. But I think it's sort of intuitive what we do here. Okay? I don't know if anyone has any guesses, but at the very least, we're going to find pi over 6, 30 degrees. Okay? So 30 degrees kind of looks like here. And then we go backwards. It's not necessarily down, because down would sort of be like here. We just go backwards 2. So instead of going here 2, we go the opposite direction. Okay. Negative means backwards for polar coordinates. Okay. So instead of pi over 6 and forwards 2, which would be here, we go pi over 6 and backwards 2. So if you think about, right, if you thought about a dotted line right here, instead of going here 2, we go the opposite way 2. The dotted line is way too hard to see on this camera. I drew it very faint. All right, so the last problem, part D, it's going to be 2 comma 7 pi over 6. So again, You can have bigger angles. You just find 7 pi over 6, then find 2, and you're good to go. So 7 pi over 6, 7 over 6, that's more than 1. So it's more than 1 pi. So we're going over 180 degrees. How much more? Pi over 6. Pi over 6, radius 2. That's right here too. Right? We're on the circle of radius 2. The angle of 7 pi over 6, which is going over pi, and then pi over 6 more. So C and D are actually the same point. Yeah, you can kind of think it in the same form of a negative hypotenuse. Yeah. When we plot points on the xy plane, we always treat the hypotenuse as positive because that relates to the angle. If we dealt with negative hypotenuses, then that would change the angle, just like here. So these are the same points, C and D. Just one has a positive radius and one has a negative radius. Okay, and that's how. And you'll see this is very natural. And by natural, I mean not natural, but natural is a very mathy person word to use. It works. It's consistent. And when we get into later examples where we convert, and by later examples, I mean the very next example, where we convert, you're going to see why having a negative radius, meaning this, kind of works mathematically. Okay. So that's what we're getting at. That's how you plot things. Now, for the rest of the section, we're just going to be converting between polar coordinates and rectangular coordinates. We're going to be converting points. We're going to be converting equations. We are skipping the section on graphing in polar coordinates. We might or might not have skipped that if we were still in class. But it does not make sense to do a graphing section if you don't have polar paper. Okay. And I guess I could just give you things to print out yourself, but it's much easier to do in class, and it's not that important. So we'll be going directly to 10.5 after this section. So the rest of the section is conversions. And you don't have to memorize anything here because you already know trig. Okay? As long as you remember your trig, you're going to be good to go. So specifically, right? If I look at a point in rectangular coordinates, let's call this point x comma y. We can also think about this point as r comma theta. Okay? And if x is y's, we could draw a triangle. Yeah, triangle. Right? We could draw a triangle where this is the x coordinate, this is the y coordinate, the hypotenuse is the radius, and theta is just this angle. Okay? So you just have to remember your trigonometry to be able to convert. Because what does trig say? How do we relate this angle with these sides? Well, we could use cosine and sine. Right? What is the cosine of theta? It's adjacent over hypotenuse, x over r. We can multiply both sides by r to get x is equal to r cosine of theta. And this is a very common thing to use when converting between polar and nonpolar. Both of these are pretty good. This is the more common one. And remember when we were talking about the unit circle, right? Again, all the way back to chapter 7. When we talked about the unit circle, we said x was just cosine of theta. Well, that's for the unit circle. The radius is 1. For any circle, it's r cosine theta, right? And we could set up a similar equation with sine, right? The sine is opposite, which is y, over the hypotenuse, which is r. Or again, we could do similar things, multiply by r. Y is r sine of theta. And these are technically all you really need. These are all you need. But there's a third one that can save you a little bit of time sometimes. If we don't want to think about thetas. If we don't want to think about thetas and we want to relate x, y, and r, There's a really nice equation that we know called the Pythagorean theorem. X squared plus y squared is equal to hypotenuse squared. Okay. R squared is equal to, I have all my r's on the right. Let's be consistent. We also know that x squared plus y squared equals the hypotenuse squared. So these are very useful. And these also useful, but not as much. Okay? If you forget, just remember your trig. Remember your trig. And you can come up with them again on your own. So let's see how this works. You are going to laugh when you see how easy this is. This is example 2. You might not laugh, but you might. If anyone has a chuckle at home for example 2, share it. Share your success. Okay. So example 2 is convert from polar to rectangular. So it's kind of one thing that's kind of weird, by the way. Part A is going to be 3 pi over 2. Right, is the format we use to write these points is the same whether you're in polar coordinates or rectangular coordinates. Okay, right? Polar is r theta. Rectangular is xy. But, right, when we have numbers here, you don't know whether that's an r or an x. So you have to use context clues. Because it says convert from polar, we know that this is our r and this is our theta. Okay? So we just need to, figure out what is x. If only we knew a very useful equation that related x, r, and theta. And of course, we do, right? So x is equal to r cosine of theta, and r is 3. Theta is pi over 2. All right. We can do it this way. Another way of doing this is we could have graphed this. That doesn't work for everything, but we could also have graphed this. Theta is pi over 2. So we go up pi over 2. We have no x coordinate here. Okay? Or you could say cosine of pi over 2 is 0. A lot of different ways of solving this. Okay, so the x coordinate 0. So in Cartesian, the x coordinate 0, and we do similar thing for the y. Y is r sine theta. So y is r sine theta. We just do the same thing. 3 times the sine of theta, which is still pi over 2. Sine of pi over 2 is 1. So y is 3. Okay? And indeed, if you plotted these, you would get the same point. If you plotted on a circle, pi over 2, right? The radius 3 is this circle. Pi over 2 is 90 degrees. It'd be right here. Or if you plotted the point 0, 3, you're also right here. So whether you plot it in Cartesian, rectangular, or polar, the point will be on the same place. Okay? A good way to check your answer. So I mentioned that negatives kind of work well and are consistent. Let's see that with part B. Part B is negative 2, 0. And again, this is our r, and this is our theta. Let's change theta. Let's do a different example here. Let's have theta be like pi over 3. Okay? So again, we just do the same thing. We use our formula for x, we use our formula for y, we get our answer. X is our cosine of theta, which is going to be negative 2 times cosine of pi over 3. Cosine of pi over 3, by now, probably familiar, it's 1/2. Negative, or you can use a calculator. Negative 2 times 1/2 is negative 1. So that's the x coordinate. Ooh, that is a weird one. And similarly, right, y is r sine theta. which is negative 2, times the sine of pi over 3, which is root 3 over 2. And you get negative root 3. Okay. So again, in Cartesian coordinates, you can very easily see what quadrant it is. The x coordinate's negative, the y coordinate's negative, we're in the third quadrant. Here it's a little harder to see that you're in the third quadrant. But again, if you tried to graph this, right, you'd find where pi over 3 is, 60 degrees, and you go backwards, negative 2. You'd be right here, which is also in the third quadrant. Okay, so just another way of kind of checking your answer and making sure whether things make sense or not. That's that example. Okay. So we're going to do one more problem, example 3, and then we're going to be done. There's only one more example after this, right? Example 4 is very long though. I don't want to start example 4 today because it has a lot of parts. We'll spend tomorrow doing example 4 and starting the last section. Okay, so let's go backwards. Backwards is a little bit trickier, but it's not too bad. Convert from rectangular to polar. Okay, where the point here is 3, 3. Again, this is our x coordinate, and this is our y coordinate. So we can do things a couple different ways. You can go to these formulas, but these formulas aren't as useful, right? If x is 3 and y is 3, we could plug that in. Then we get a system of equations, and sure, we could solve the system of equations, but it takes a lot of time. It's easier to think about these for the picture, right? Pictures are helpful here. What kind of picture? A triangle. All right. So 3, 3, say that's right here. The y coordinate is 3, the x coordinate is 3. We need to know what is this angle and what is the hypotenuse. Well, we'll use Pythagorean theorem and we can use some trig. Okay. So in polar, we're going to get an r comma theta. What is r? Well, r squared is equal to 3 squared plus 3 squared. R squared is 9 plus 9. R squared is 18. R is the square root of 18. Again, square root both sides. We need a plus or minus. We don't need a plus or minus here because the hypotenuse is going to be positive. It doesn't have to be, right? If you had r being negative, you just have a different angle. And simplify this, right? This is 9 times 2. This is 3 root 2. So our radius is 3 root 2. And we use trig to find out what we have. The astute trigonometry student is going to go, wait a minute, I know what the angle is, right? Because this is an isosceles triangle. These two sides are the same. This is a 45, 45, 90 triangle, okay? So it's pi over 4 is our angle. But if you didn't know that, say you didn't know that, you could say tangent of theta equal to 3 over 3 and solve this equation. When is tangent of theta equal to 1? Okay, and you'll get theta is pi over 4 that way. So a couple ways of approaching this. But that's the first half of the section. Okay, so real quick, let's review where we're at right now. So on Wednesday, homework 10.2 is due, as well as your quiz, which I'll be writing later today. Okay, that's what Wednesday is going to be for what's due. If you got at least an 80% on your last exam, the exam that was last week, then you'll automatically get credit on your homework. But again, I highly recommend that you at least do some problems where the problem gives you all 3 sides. Those ones are a little trickier for law of cosines. All right. And then next week, you'll have 10.3 and 10.5 that are going to be due. And you'll have a final exam. This will be your last quiz. So next week will be your final exam, and it will cover everything from the entire class. As always, if there are any questions, send me a message on Discord. Send me an email if you prefer email. Or you can ask before class, because I do usually start about 10 minutes early. But yeah, that's it for today. Anyway, good luck. Yes, final review packet will be uploaded by Wednesday. I'm trying to get it done today, but I'm not going to commit to that. I'm trying to get the final packet done today. But if I have more work than I think I do, then it'll be done by Wednesday. Yes, Ashton, you did. Send a color was today's. We did it early. I was tricky. All right. Have a good day, everyone. And adios.